Okay, and welcome back to another video on the Maths channel. It's your teacher, Miss Lim here. In this video, we're going to be looking at rational numbers and irrational numbers. So by the end of this lesson, you'll be able to define real, rational, and irrational. Understand why all integers, terminating decimals, and recurring decimals are considered rational. Simplify surds, and express surds as a square root of a single positive integer. So let's have a look at the first part of this lesson. Definitions. All real numbers can be located as a point on a number line, and real numbers include rational numbers, which can be expressed as fractions. So just remember that rational means I can write it as a fraction. If I can't, then it's irrational. So for example, 3/7, that's already a fraction. Same as the next one. -3, I can write that as a fraction. It's -3/1. 1.6, I can write that as a fraction as 1 6/10. 2.7 repeater is a fraction. I can write it as a fraction. 0.19 repeater, I can write as a fraction. Okay. The decimal representation of a rational number is either a terminating or a recurring decimal. Right, irrational numbers are numbers that can't be written as a fraction. Okay, for example, √3. If I type √3 in my calculator, I get that. It doesn't end, it actually goes on forever. Our calculator just doesn't have enough space to show everything. There's no pattern. If I press my S to D button, it doesn't work. Can't write it as a fraction. Okay, same as -2√7. Can't be written as a fraction. Or √12 -1. Can't be written as a fraction. Pi. Can't be written as a fraction. So, all of these are examples of irrational numbers. And the decimal representation of an irrational number is an infinite, non-recurring decimal. So we can see here, this will actually go on forever, but it doesn't, there's no repetitive pattern, no recurring pattern that we can see. Same with all these other examples, there's no recurring pattern that we can see. Alright, and the last one here are surds. Surds are irrational numbers that use a root sign. For example, √2, 5/11, etc. Now, these ones down here, even though they use a surd, or even though they use a root sign, they are not surds because √4 is equal to 2, and we can write that as a fraction. The cube root of 125 is equal to 5, and we can write that as a fraction. Okay, the -4th root of 16 is equal to -2, and we can write that as a fraction. So all of these are not surds, they are not irrational. Right, so express each number as a decimal and decide if they are rational or irrational. First one, we've got -√3. It's about -1.73. Okay, so I'm going to write it's approximately equal to -1.73 to 2 dp. And it seems like there's no recurring pattern. It looks like it goes on forever. Let's just double check with the S to D button. Doesn't turn into a fraction. So this is irrational. Question B, 137%. We know that is 1.37. This is a terminating decimal, so it is rational. Okay, all terminating decimals can be written as a fraction. So we've got 1.37. Oh, yep, see, I can turn it into a fraction. Right, 3/7, that's already a fraction. So we already know this is rational. But let's just see, right, 3/7, what is that as a decimal? 0.428571, 428, oh, it's running out of space to repeat itself. It should say 57, but because there's not enough space, the 7 rounds to 5 up to a 6. Okay, so it might not look like it repeats, but it actually does. Okay, 0.428571. 42857 and then it repeats itself. So my all integers terminating and recurring decimals are rational. An integer is a whole number. Okay, it can be positive or negative. For example, let's just say 3, -7, right? 2 examples. Now, integers are rational because they can be written as fractions, right? 3 over 1, -7 over 1. Or I could written 3 as 6 over 2, because 6 divided by 2 is 3. Or I could have written -7 as -21 over 3, because -21 divided by 3 is -7. Right? Lots of different ways, but I can write them as fractions. So all integers, if it's a whole number, can be written as a fraction. Here's more proof that terminating decimals are also rational. Okay, terminating decimals are decimals that don't go on forever. Okay, they have some sort of end. They terminate. For example, let's say 0.6, or let's say 0.32. All right, so they are rational. Let's change this to 7.32. Okay, so 0.6 I can write as a fraction, 6 over 10. Okay, 7.32 I can write as a fraction as 7 and 32 over 100. Okay, or 732 over 100. Okay, same thing. I want to do 7.32 S to D. Okay, it simplifies it because I can divide it by 4. Okay. Recurring decimals. Recurring decimals are decimals that go on forever. And have a recurring pattern. I'm just going to write it up here. A recurring pattern. Okay, so for example, we can have 0.3 repeater. Or let's say 0.7272. Okay, I might just use this notation. Okay, they are rational because they can be written as fractions. So, I've got 4 examples here. We'll have a look at the first one, 0.3. So what I'm going to do in order to prove that this is, in order to prove that this is rational, that I can write it as a fraction, I'm going to do this algebraically. We've got 0.3 repeater. We're going to let x equal to 0.3 repeater, which is technically 0.333 forever. Okay. So what I'm going to do with this is I'm actually going to multiply this by 10. Okay. When I multiply this by 10, I'll get 10x. And when I multiply this by 10, I'll get 3.333 forever. So what I can do now is I can subtract these two lines. 10x minus x is 9x. Can you see how all these 3's line up? So when we subtract them, they're all going to cancel each other out, leaving me with 3 minus 0 is just 3. So x is technically 3 on 9, or 1/3. Okay, so 0.33333 forever is equal to 1/3. So here's my question to you. Is 0.9 repeater, so 0.99999, is that equal to 1? I want you to pause the video, maybe think about it. If you're with some friends in a classroom or something like that, maybe discuss, is 0.9 repeater actually equal to 1? Yes or no? Alright, I hope you've had some good discussion on that. The answer is yes, it is. 0.9 repeater is actually equal to 1. Now you might be wondering why. They're not the same. Come on. Well, I've proven already that 0.3 repeater is equal to 1/3. If I were to multiply 0.3 repeater by 3, right, 0.3333 forever, and multiply that by 3, won't I get 0.9999 forever? I would, which is 0.9 repeater. Well, if 0.3 repeater is 1/3, and I times that by 3, oh, that gives me 1. So we can see here, 0.9 repeater is actually equal to 1. So let's have a look at question B. Right, we got 31.9 repeater. We're going to let x equal to 31.999 forever. And I'm going to times this by 10. So x times 10 is 10x. 31.9 repeater times 10 is 319.999 repeater. Okay, it's going to go on forever. And so now we can subtract 10x minus x is 9x. All these 9s cancel each other out. Okay, they perfectly line up. And so now we're going to do 319 minus 31. 288. So x is equal to 288 over 9. Which you might be thinking, if I were to divide that by 9, oh, I get 32. I don't get 31.9 repeater. What's going on here? Well, that's because 0.9 repeater is equal to 1. So technically, this number here, 31.9 repeater, is actually equal to 32. Right? And we can write that as a fraction. So it's rational. Okay, let's have a look at C. So here we're going to let x equal to 20.787878 forever. But I'm not going to times this by 10. Let me show you why. If I were to multiply by 10, I'll get 10x is equal to, if I times this by 10, I'll get 207.878787 forever. But they don't line up. So I cannot subtract them. So instead, I need to multiply by 100. If I multiply by 100, then the decimal will move 2 to the right, leaving me with 2078.787878 forever. And now when we subtract, these will cancel each other out because they line up perfectly. So when I subtract, I'll now get 99x. Okay, 100 minus 1 is 99. 2078 minus 20 is 2058. And now I can divide both sides by 99. And that's my answer. And we can double check. Yep, 20.787878. It says 79 there, but that's because it rounds it. Alright, now, here is my advice to you. This is my tip. Because in A, there's only one number being repeated, just a 3, we times by 10. In B, only one number is being repeated, so we times by 10. In question C, two numbers are being repeated, so we times by 100. In question D, 3 numbers are being repeated, so what do you think we need to multiply x by? Okay, we should be multiplying by 1,000. So if we let x equal to 12.401401, etc. And we times it by 1,000 to give us 1,000x. If we times it by 1,000, we move the decimal place to the right 3 times. We'll get 12,401.401401 forever. And now we can see, oh, it lines up perfectly when we subtract these, we'll cancel each other out. So 1000x minus x is 999x. 12401 minus 12 is 12389. And now we can divide by 999. And we can double check our answer. 12.401414. Alright? So, that's how we show that recurring decimals are actually rational, because we can express all of them as fractions. Alright. Let's have a look at simplifying surds. The last two bits, nice and easy. Simplify the following. Root 32. Now, whenever we want to simplify surds, we always want to think about what two numbers multiply to that number underneath the surd, where one of them is a square number, so we can square root it. So you might be thinking, okay, yeah, root 4 and root 8. 4 times 8 is 32, and I can square root 4. But we want to actually use the biggest number if possible. Alright? So the biggest square number. So yes, I know 4 is a square number, but so is 16, because I can do 16 times 2 as well. Root 16 times root 2. Now, we know the square root of 16 is 4, so technically it's 4 root 2. And we have simplified it. In question B, we've got 3 root 200. That means 3 times the square root of 200. Well, 200 I can split into 100 times 2. And I can square root 100. So this is technically 3 root 100 root 2. Well, square root of 100 is 10. 3 times 10 is 30 root 2. 30 root 2. Question C. Root 40. What can I divide that into? Okay, what two numbers multiply to 40, where one of them is a square number? I can think of 4 and 10. So we get 5 times root 4 times root 10 over 6. Well, the square root of 4 is 2. 5 times 2 is 10. So we've got 10 root 10 over 6. 10 root 10 over 6. And now I can simplify this. And when we simplify, we're only looking at what's on the outside, right? Okay, what's on the outside. We don't look at what's underneath the surd. So 10 over 6, that simplifies to 5 over 3. So this is 5 root 10 over 3. And this last one, root 75 over 9. We can actually split this up as, let's use blue. We can split this up as root 75 over root 9. Now I know the square root of 9 is 3, so I can just put that there. But root 75, can we simplify that? Well, I know 25 times 3 is 75, and I can square root 25. So this is root 25, root 3. Okay, square root 25 is 5, so we get 5 root 3 over 3. And that's it. Alright, last bit for this lesson. Expressing surds as the square root of a single positive number. Express these surds as the square root of a positive integer. So here we've got 2 root 5. I want it as the square root of something only. I don't want anything on the outside. So what I need to do is I need to square this 2. Right? 2 squared is 4. So technically 2 is equal to the root 4. Okay, the square root of 4 is 2. But we're multiplying by root 5. And so now we've got root 4 times root 5. That's the same as saying root 20. Done. Question B. 7 root 2. What are we going to do to that 7? Well, 7 squared is 49. So the square root of 49 is 7. Times it by root 2, because that's what it says here. Well, 49 times 2 is 98. So we've got the square root of 98. And that's it for this lesson. So let's recap what we looked at. So we looked at definitions. Okay, we said that all real numbers can be written on a number line. We said rational numbers can be written as a fraction. Irrational numbers can't. Surds are irrational. They can't be written as a fraction. We showed you why integers, terminating decimals, and recurring decimals are rational. We showed you how they can be written as fractions, right? And this is really important. Yeah, in an exam, you could definitely be asked this, showed algebraically that this recurring decimal is rational. Okay. We looked at how to simplify surds. Ask yourself what two numbers multiply to what's underneath the surd, where one of them is a square number, so I can square root it. Okay. We have a look at all of these. That's a square number. That's a square number. That's a square number. That's a square number. Okay, we can square root all of them. And we also looked at how to express surds as a square root. Alright, so I hope you found this video helpful. If you still have any questions, please comment down below and I'll get back to you as soon as I can. If you like this video, if you found it helpful, please give it a like. And if you would like more content, please subscribe so I have an idea. Thank you, and I'll see you in the next video. See you.